Hey, welcome back. So we've got another angle of twist problem. Now, when you look at the diagram, it probably looks like one of the power transmission problems like we did a couple videos ago, but really it isn't. And it's not because, as you can see, in the problem, they've already done all of the transformation of the power takeoffs. So everything is already provided as a torque. So really they've already done that extra step to get from power down to the shaft that we have. So really we're jumping in, we're looking at a free body diagram, we have a number of torques, and then we're going to look at some relative displacements on the shaft. And so let's get on with that. So let's jump down to the free body diagram. I'm going to add the uh, externally applied torques or loads. So we have a torque at A, a torque at C going in the other direction. I'll go back and put in the values in just a second here. And then, of course, we have a reaction at the support at E. It's going the other direction. And so what do we have? We have our torque at E. Then we have some values here. We should put them in. I've labeled the free body diagram because it's all torques as Newton meters, so I don't have to put in all of my units on every one of these individually. And we've drawn our x-axis, positive right, so I think we're all ready to go. So we can get right on to solving for that reaction that we don't know. So we apply our one equation of static equilibrium, which in this case is the sum of the torques about the x-axis, set it equal to 0, and then working left to right, we'll work at 150 Newton meters. Negative, we'll add to that 280 Newton meters, add to that 40 Newton meters, and subtract our torque at E. And it's our only unknown. We can isolate for the torque at E and resolve that down, and we get a value of 170 Newton meters. So I'm just going to write that in here, 170 Newton meters. So we have a fully resolved free body diagram, so we can just go ahead and build our torque force diagram, and I'm just going to use the graphical method to do that. So we've seen this once before, so I'll go through it fairly fast. If you didn't see that video and you need a bit more of a slower explanation, I'll put a card up here taking you back to that video so you can jump in there. So we have a negative 150, so our internal torque will be a positive then. So I'm going to draw in our 150. We have no change between A and C. So we'll stay at 150. I'll put a value in here of 150, and then 280, it's a positive direction, so that's going to be negative to our internal torque, so that's going to push this down negative. And it's going to go to negative 130. That's 150 minus the 280, things down to negative 130. There's no change between there and D. And then we have our 40 takes us negative additional 140 down to negative 170. And again, constant between there and our support, which is a value of 170, which takes us up to 0, which is a good thing. Otherwise, we would have made a mistake along the way. So I'll just close that off to finish our diagram. So we have our torque force diagram. So we know what the torque is everywhere along the length of the shaft. And so we can calculate our angles of twist in successive sections of uniform torque and geometric properties and all of those things, as we've done once before. So let's label. So we have our angle of twist. And so in this case, we're interested in the overall angle of twist between A and E, and that is going to be equal to the or the sum of the angle of twist between A and C plus the angle of twist between C and D plus the angle of twist between D and E. And because we're going to want to graph it, I'm going to calculate each of these ones independently so we can get the steps along the way so we can graph it. And just as a reminder, we know that the angle of twist in any one uniform section is equal to the internal torque in that section over the length of the section divided by the polar moment of inertia and the shear modulus. Now, the polar moment of inertia, as you can see up here just under the statement of the problem, I went ahead and calculated that for a shaft. We've done that before. There's not a lot of sense in repeating it. We know that the formula is pi over 2 c to the fourth, and I substituted in 0.007 meters for our radius and calculated that out. So there that is. So we're ready to go. We're just going to work through each of the sections individually. So I'll start with our phi A to C. And so our internal torque is 150 Newton meters. And that's right off our torque force diagram. And the length over which it's applied is 0.4 meters. And then we have to bring down our J, 3.771 times 10 to the minus 9 meters to the fourth. And our shear modulus then, go to the question, 80 GPa. So that's 80 times 10 to the sixth pascals. And that will calculate out and give us an angle of rotation between A and Z of 0.1989. That would be radians. And then, of course, to this, we have to add the angle of twist between C and D. So off our torque force diagram, we see we have a torque of minus 130 Newton meters. So it's going to be twisting it the other direction. And the length over which it's applied is 0.3 meters. And we have the same J and G. And that calculates out to be an angle of twist of negative 0.1293 radians. And finally, for our last section, we have a torque off our torque force diagram of minus 170 Newton meters, and it is applied over 0.5 meters. And divide that through by our J and G. They're the same, so I'll just copy them down here from above. No surprises there. And we get an angle of twist between D and E of 0.2818 radians. And I'm just going to remind ourselves or label these. That's AC, that's CD, and that is DE. And when we sum those up, as we set out to do, we get 0.2121 radians. Now we have to transfer this to our angle of twist diagram to track it. And of course, when I calculated these out, I calculated them kind of left to right, right? A to C is a positive angle of twist. So if I was drawing it the other way, it would go kind of negative. So for example, in D to E, so I'm starting at 0 at my support at E, and to go D to E would be negative 0.2818. So I'm going to have to be going up to go from E to D. And so that's just a little quirky thing to watch as we draw these up. So we have to go up to 0.2818. So probably about there. And I'll draw that in. 0.2818. And then we're going in the same direction, so we continue to go up an additional 0.1293, which should take us up to, if I calculated that right, value of 0.4111. And then that 0.1989 between A and C would be a negative of the same between C and A. And so we draw that in here, and that takes us down to our total value, which we started off was 0.2121 radians. So there we go. We've got our angle of twist all around it. Now, just for an interesting twist, they say, okay, calculate the displacement at P. And P, as you see on the diagram, is that little tooth out on the gear at A, so out and away. So this is not much of a mechanics and materials problem. It's more of a geometry problem. So really, let me just draw out so if this is my gear that we're talking about, and my pen back, so I'm just going to have my shaft going off here. So we have our tooth at P here, its original position. The shaft has an angle of twist of some value, and that is our angle of twist in here. And so to calculate our displacement here, so that's our displacement at P, we know our angle of twist from the previous calculation is 0.2121 radians. Our displacement, because of small angles, has to be our angle of twist multiplied by the radius of our gear. And so that is equal to 0.2121 radians multiplied by our radius of 100 millimeters, given in the diagram. And that gives us a total displacement of the tooth at P of 21.2 millimeters. And so let's just note our major solutions here, and that's it. Looks like a power problem. It's not a power problem. They did that extra step for us in formulating the question. This was a straight up free body diagram, torque force diagram, angle of twist between the various sections, and then that one little quirky calculation down at the end to get the displacement of that tooth. So that's probably puts a lock on shear stresses due to torque, due to torsion, and angle of twist. We're going to have to look at some statically indeterminate problems. So we've got those coming up. We're going to do at least a couple of those because they can be a little bit quirky and they take a little bit of practice in order to get right. But otherwise, we're almost done torsion.